given two real numbers a and b, we can say if a is less than or equal to b or b is less than or equal to a. That means that we can say if a is larger or b is larger. Suppose that we have given two sets. How do we say if one set is bigger than the other set? One notion is to say if one is a subset of the other. If capital A is a set and capital B is another set in such a way that capital A is a subset of capital B, we may probably say that A is a smaller set compared to B. But this is not always going to happen. For example, suppose that A is a set of some elements and B is a set of some different elements. For example, if we take A to be equal to set 1, 2, B to be equal to set 2, 3, 4, then we cannot make this comparison. One way in such cases is probably to compare the number of elements in sets A and B. For example, for in this given example, we have A consisting of two elements because it's 1, 2, and B consisting of three elements. And in that sense, probably we may say that A is somewhat a smaller set compared to set B. So we are going to see how to make comparisons based on size of sets. But remember that when we have infinite sets, for example, suppose all rationals, suppose all integers, the set of all natural numbers. In this case, we cannot definitely say that how many elements are there, and because there are more elements in one set compared to other, one set is going to be larger than the other one. In all these cases, we would like to make a discussion about how to compare two sets, even if the sets are infinite in number. Suppose that we consider capital A to be the set of all teachers in our college and capital B to be the set of all students in the same college. In this particular case, we have capital A consisting of around 30 or 40 members and capital B consisting of around 500 members. Therefore, we can see that the set A is going to be much smaller compared to the set B. So this is the way of comparison that we wanted to make depending upon the number of elements in the set in the sets A and B. These are the two sets we are going to compare. In this case, we have A is going to be smaller than B as far as the sizes of A and B are considered. A is smaller than B if we consider the number of elements in both A and B. The cardinality of a set when we are considering a finite set is the number of elements in that set. So cardinality of a finite set equal to number of elements in set. So one way to compare two finite sets is, as we said, to look at the number of elements in the each of these sets and say if the number of elements in one set is going to be less than or equal to or greater than equal to the other one. Therefore, we are basically comparing the cardinalities of two sets. So the cardinality of A and cardinality of B that we have taken here, cardinality of A is going to be less than cardinality of B. Now, is there any way to compare two sets without actually counting the elements in those two sets? For example, suppose that we have an auditorium consisting of around 400 seats, and we know the number of seats in that auditorium. And suppose that some people are about to enter the auditorium. So if they are entering and after they enter, how can we know that if the number of seats and the number of people entered are the same or less or more? So how do we make the comparison? One way is to, of course, we know that number of seats is 400, and therefore if we count the number of people entering the auditorium and if we find the number of people to be something less than 400, something suppose that it is going to be 300, for example, then number of people is less compared to number of seats. And if the number of people is 500, say, then number of people is more than number of seats in the auditorium. The question is, can we make the comparison between number of seats and number of people by saying that number of seats is more compared to number of people, or number of seats is less compared to number of people, without actually counting the number of people and number of seats. One obvious technique is probably to suppose that we ask everyone entering the auditorium to just be seated in such a way that in each and every seat only exactly one person is sitting, and we are assuming that the seat is in such a way that it can accommodate exactly one person. Suppose that we ask everyone in the auditorium to occupy one seat, and suppose now that every seat is occupied and still some people are standing. It means that number of seats is less than number of people. If we observe that all seats are occupied and some seats are, all people have already occupied seats and some seats are still vacant, it means that number of people is less than number of seats. If you see that all seats are occupied, not a single person is standing, it means that number of seats is going to be exactly equal to number of people. See, what we exactly did is we didn't actually count the number of seats or number of people. Instead of that, we assigned to each person one seat. The assignment finally resulted in either finishing all the people and some seats are left, or all seats are finished, some persons are left without a seat. In either case, we have not performed any counting. Instead of that, we just try to assign seat to people and observe if somebody is left or not, if some seat is left vacant or not. This is another way of finding out or comparing sizes of two sets without actually counting. And what we basically did is we tried to establish a function between number of people and number of seats, not number of people, between the set of people and set of seats, and try to see if it's a one function or onto function, or one and onto function. If it's a one and onto function, we have number of seats equal to number of people. If it's a one function or if it's an onto function, the situation is different. Now we are going to precisely define one onto functions and one and onto function. That's what we are going to do next. We now have a standard set theoretic definition of one-to-one function. A function f from set A to set B is one-to-one. In short, we write using the symbol if A1 not equal to A2, where A1 and A2 are elements in A, implies that f of A1 not equal to f of A2. So we say that a function is one-to-one if A1 and A2 distinct implies that their images are also distinct. So an example for such a function is probably to consider the set of all capitals of countries in the world to be capital A and not necessarily set of all. Suppose that we are listing in capital A some uh, capitals of countries, and suppose that in B we are listing all the countries in the world. So we have, if A1 is one capital, A1 corresponds to exactly one country. Therefore, if A2 is another element different from A1, that will correspond to another country. So f of a1 will not be equal to f of a2. That means countries corresponding to a1 and a2 will be different if a1 and a2 itself are different. This is an example for one-to-one function. A equal to set of some cities in the world. B equal to set of all countries in the world. So suppose that we define f like this. F of A equal to country where A is located. Since we know that one city can belong to exactly one country, so this function is one. But on the other hand, suppose that we are defining G from B to A as G of B, that means a country, equal to a country in B. This function is this definition is actually not going to be even a function, because suppose that, for example, uh, country B is equal to India. Suppose we have B country India, and suppose that we have in A Trivandrum and New Delhi belongs to A, then it is not very clear that if G of B is going to be equal to Trivandrum or New Delhi. Therefore, this definition of G is not even a function. This is not qualified to even become a function. Another example probably is the following. Suppose that we have A equal to set of all students in a class, B equal to set of all benches in the same class. Suppose that F from A to B defined by, if A is a student, then f of A is the bench B where A sits. So f of A is a B if B is the bench on which A sits. Is this a quantum function? So we cannot actually say that, because it can happen that there may exist two students, A and A dash, sitting on the same bench. Therefore, f of A, therefore f of A will be B, and for the student f of A dash also will be B, but A not equal to A dash. Therefore, this function is not going to be, this function is not 1. On the other hand, now suppose that we consider G from B to A. Once again, as in the previous case, if we define that G of B is uh, student sitting on B, then there may be more than one student sitting on this bench B, and therefore we cannot have a unique answer in this case. Therefore, G of B we cannot uniquely determine, and therefore G is not even a function. Example, other one. Suppose that instead of bench, A equal to set of all students in a class, and B set of all chairs, single seat. So in this case, corresponding to every student, we can find one chair. Therefore, we have this function f from A to B, where f of A is the chair of A. This function is 1. F is therefore 1. Now we have the other definition. F from A to B is said to be onto or surjective. For a one-on function, we say that it is actually an injective function. It's said to be surjective or onto if for B in B there exists A in capital A such that f of A is equal to B or B equal to f of A. So corresponding to every element in capital B, we can find some element in capital A that B becomes the image of that A. Example. Suppose that A is the set of all countries, B equal to set of some people. Now define F from B to A by F of B equal to A if B is in country A. Is this an onto function? See, we have taken A to be the set of all countries and B to be the set of some people. So it can happen that we are choosing some country on the right side. Say, suppose that we are choosing New Zealand, and it can happen that there is nobody from New Zealand in the set B. Therefore, this function is not an onto function. On the other hand, suppose A equal to set of all students in a college and B equal to set of all classes. So F from A to B, F of A is the class to which A belongs to. So every class must be having at least one student, and therefore, if we take one small b from capital B, that's a class, you can find correspondingly at least one student in the set A. Therefore, F is owned. Now we have the final definition in this line. Here from A to B is a 1-1 correspondence from A to B if F is both 1-1 and onto. If you have F both 1-1 and onto, we say that it's a 1-to-1 correspondence. An example from mathematics. F from the set of all integers to the set of all even integers defined by f of n equal to 2n. So this is 1-1 because suppose f of n1 equal to f of n2 for some n1, n2, z. Then we have 2n1 equal to 2n2 or 2 times n1 minus n2 equal to 0. Since 2 is not equal to 0, n1 minus n2 must be equal to 0. Therefore, n1 equal to n2. So if we get f of n1 equal to f of n2 implies that n1 equal to n2, or n1 not equal to n2 implies that f of n1 not equal to f of n2. This is a standard technique in establishing if a function is 1-1 or not. So instead of proving that, instead of taking n1 not equal to n2 implies f of n1 not equal to f of n2, we usually start with f of n1 equal to f of n2, and we will show that n1 is equal to n2. So f is 1. What about onto? Suppose we choose, suppose x belongs to z, and therefore how does x look like? X equal to some 2m for some m integer. But then we know that m is an integer, therefore f of m equal to 2m equal to x. So corresponding to every x in 2z, we can find an m in z. Therefore, this is arbitrary, this x is arbitrary, therefore f is onto also. So this function is both 1-1 and onto, therefore f is a 1-to-1 correspondence from z to 2z. We established.